Okay, we're gonna go ahead and continue with Nathan Wiatrek. His presentation is titled "Creating a Spacecraft Digital Twin for Flight Software."
All right. Good morning, everyone. My name is Nathan Wiatrek. I am a senior research engineer here at Southwest Research Institute, where I primarily focus on embedded systems for spaceflight software. Today, I'm really excited to be talking to y'all about creating spacecraft digital twins for flight software. Digital twins have been a big topic at this conference so far, but what exactly is a digital twin? So a digital twin is a software representation of a physical system. These are used all over. There's digital twins for automobiles, there's digital twins for human patients. But for flight software, a digital twin gives us two things. It reduces time and it reduces cost. It reduces time for us to develop, test, and demonstrate flight software by eliminating hardware resource constraints. You don't have to fight over a flat sat when you have multiple engineers working on various aspects of the software. You can demonstrate your progress in weeks, not months or years to your clients if you have a ADCS algorithm that you want to show off. You can run multiple digital twins in real time or faster. Gone are the days of having to take 4 seconds in real world time to do 1 second in the simulation. You can do it in real time or faster. And most importantly, you can build a library of reusable software for simulating hardware. So let's say you're doing a mission and you have a very specific sensor that you want to use. The first time you're doing it, you're going to model its inputs, its outputs, how it's actually interacting with your system. And then say the next mission, you really liked that sensor and you want to use it again. Well, you just plug in that library that you already made into the next system and you're already off and running. And it can reduce costs for us for mission operation sustainment. You can avoid costly replacements due to hardware obsolescence. Many of us have had satellite missions go on longer than anticipated. Maybe you put your flat sat away in a closet. Now you have to bring it out and you reconnect it. Your cables are broke. The battery on one of the computers is totally gone for some reason. You don't have to worry about that if you're using a digital twin. And it provides a high fidelity model for support, verification, and validation, and provides that early on in your cycle. In other words, a digital twin takes this, a flat sat, which this is actually MMS, which there's pictures outside if you want to see more of it, where it has many components that are sprawled out across 2 different tabletops, and they're all connected with love and care through these very fancy cables to each other, and it turns it into this. This is a visualization of a satellite that is in orbit around the Earth. We can see that we have a lot of diagnostic information top left, such as simulation time, and we can really see what our satellite, what our algorithms are actually doing. So today I'm going to be talking about what is a digital twin, why it's important. I just covered that. Hope we all understand that it's super exciting. I'm going to discuss our satellite under test for creating this digital twin. I'm going to talk about the components of our digital twin and how we are porting our ADCS system to 42, which is one of the components. At the very end, there will be time to discuss the next steps for this research, as well as have time for questions. So this is Cygnus. Cygnus is our satellite under test for this research. It was originally launched in December of 2016 and consists of 8 satellites. It has basically just passed its 7.5 year out in space. It was originally designed to do advanced forecasting and tracking of extreme weather. But since it's expensive to put new satellites out in space, let's just leverage the ones we have. So we've modified it. We've modified the science that it is doing to go beyond just tracking extreme weather, such as helping quantify methane that is being produced by wetlands, as well as helping locate locust breeding grounds in East Africa. And the way we're able to do that is by modifying our software here on the Earth, validating that it's going to go well when it's out in space. So here's our system test bench as it currently stands. Each of these big blocks are a separate computer, and they're connected via physical cables in the case of serial I/O, or the TCP UDP blocks here. Now, just in the spacecraft dynamics simulator, which is, again, its own piece of expensive hardware, you are doing orbit equations of motion, environmental models. That gets output to the unit under test. And we're also sending data back to the CNT console, the data archive and analysis. We have the solar array simulator, the thermal simulator, the payload simulator, constellation crosslink and tracking simulation. There's a lot that goes on in one test bench to make sure this is going well. And there's a lot of cases where things can go wrong. Anywhere that you have a serial input-output, you could have a cable that is not connected exactly right, and that's going to give you bad results that maybe don't actually mean that much. And so what we're proposing is to change that bench to something that works just inside of your laptop. So we want to replace the real hardware with virtualized hardware for development and early integration and test. That way you can fully flush out your spacecraft dynamics, your thermal, your payload early on without having to wait for your hardware to get here. And you don't have to worry about the connections, which is really nice. So how are we going to make our digital twin? Our digital twin is comprised of 3 components. First is 42. 42, as was mentioned in yesterday's talk about NAS Cubed, is originally a NASA Goddard project, and it was designed and made for ADCS validation and design. One of the key quotes of 42 is that it is mostly harmless. That is, kind of true. It's a little painful. But it's really nice. It gives a great graphical user interface. In fact, it's what we saw at the very beginning. Then we have Renode and Verilator. These are our 2 software that we're using to emulate our FPGAs and our CPUs. And finally, we have NOS, which we are using to connect the flight software to simulated hardware. Here, I mean the FPGAs and the CPUs, not the sensors and actuators. We really like NOS Cubed. Learning a lot about the updates it had yesterday is very helpful for us. But there's a lot in NOS Cubed that we don't use. Our satellite does not use CFS. And so we wanted to take the parts of NOS Cubed that made sense for us and bring in things that we like. So porting our ADCS. To do this, we just extracted our relevant C code from our Cygnus project that pertained to the ADCS system. It did not rely on any operating system underneath the hood, so that was pretty painless, and just compiled it straight into 42 because 42 is open source. We created a spacecraft in 42 that resembled Cygnus. By this, I mean we could find a bunch of sensors in the 42 satellite creation file, and we could find a bunch of actuators. There were some units in these sensors, some properties that we didn't know much about at the time because we're software people. And we thought, well, these engineering units kind of make sense, but not really. Let's just plug it in. It's going to be close enough. Same with the actuators. And for this research, we wanted to demonstrate two different modes, our sun point mode and our nadir point mode. Sun point is when we are pointing our solar arrays directly at the sun, and it's our safety mode. And nadir point is where we are doing our science. So with all of that, we decided, okay, we have our satellite, we have our software, it's all in 42. It's going to work the first time exactly. So here I would like to prove that it works the first time exactly. As you can see, it's just out here in space, and it's going to go into nadir point. So it's decided, all right, it's time to spin. That's not quite nadir point. Still not nadir point. Okay, now it's upside down. And, well, are we going to get it here? No, it did not work. There were a lot of things wrong with our assumptions at the very beginning. There's a lot of things in aerospace engineering that us as flight software engineers, I don't know a ton about orbital dynamics. I know a lot more now, but we weren't successful right off the bat. So we had to decide what we're going to change. Do we change 42 or do we change Cygnus? 42 is open source. We have full access to this code. We can make it so that way it just tells us everything is fine and we're all happy. Or we can modify the Cygnus code, which we have because it is our satellite. We decided we want to modify 42 to meet our needs. The reason for this is our Cygnus code is currently out there in space, running and acting as it should. So how do we update 42? Well, we focused on individual components and interfaces inside of 42 because we found that multiple components weren't compatible out of the box. And what we mean by that is they weren't compatible for Cygnus. For example, there was a sensor that was missing in 42. There is no medium sun sensor in 42. It acts similar to a core sun sensor, but we really needed the special properties, and so we had to go in and add it. With the reaction wheels in 42 work off of a torque command where you tell it how much torque to apply to a wheel to go along an axis. In Cygnus, we actually prefer RPM commands where we just say, here's the speed that you need to go to. And we also learned the art of asking aerospace engineers for help. So I'm a software engineer. I can look at these algorithms. I can see the inputs, the outputs. I can tell you what it's supposed to do, but I don't know about these orbital planes, these perigees, the ascending nodes, all of the various body and reference frames, right-hand rule versus left-hand rule. None of that really made sense before this. So with asking aerospace engineers a lot of questions and learning a lot, we wanted to take a deep dive into the algorithms themselves to see what was going on. So this is our sun point algorithm. Up here on the top left, you can see that we have a state machine diagram, and we start out in acquisition. So in sun acquisition, we are rotisserie the spacecraft, which along this axis, until the illuminated faces are detected. So all we're doing is we're just spinning Cygnus around until we can actually see the sun. And then once we're there, we're going to go into sun hold. And that's where we scan around this z-axis over here to sense sun detection variation. We are calculating the sun gradients on our solar array, so that way we can maximize the power that we're coming in. And we're staying in that spin indefinitely, basically until it's time to get out of sun hold. There are 3 inputs and 1 output for this system. We have to deal with the magnetometer, the core sun sensor, and the solar arrays themselves. And the only actuator we're dealing with is the torque bar. And over here on the right, you can see a nicer picture of Cygnus, where this W vector is basically the sun vector. And we're spinning around this axis to calculate gradients at each of these points. That way we know where exactly we're supposed to be. And so with learning a lot of things about aerospace engineering, with modifying 42 to have the interfaces and the components that our satellite needs to use, and with understanding Sunpoint more, we threw everything into our enhanced simulation for Sunpoint. Now, right off the bat, what I want to talk about is this yellow vector that's coming straight out of Cygnus is the sun vector. And you can see that Cygnus itself is rotating along it pretty well. And up in the top left, we have a lot of diagnostic information that we added to Cygnus that we can pull out of what our Cygnus, we added to 42, my apologies, that we can pull out of Cygnus and display for us. So, such as we can see what the quaternions are, we can see how the torque bars are going, we can see the GPS, magnetometer output, and we can see what mode we are currently in up here. So right now it says we're in spin hold. What that means is that we lost track of the sun just slightly. We no longer think that we are in the optimal mode, and then it very quickly comes back into sun hold once we find that our angle towards the sun is good enough again. And so you can see that even as this replays over and over again, we pretty quickly find that we are normal to that vector and that we track it even while we're going across the globe in orbit. So that was sun point, and this is nadir point, the other mode we wanted to show off. So here we have 4 sun sensors and 2 actuators. This algorithm is actually simpler than sun hold, even though it involves more stuff. So we have the star tracker, the magnetometer, the GPS, and the medium sun sensor. And then we have 2 sets of actuators, reaction wheels, and torquer bars. And how this algorithm works is that we start with an initial state and we check if our star tracker is active. If it's not active, we go, well, that kind of sucks. Does our sun sensor, is it active? Nope, can't see the sun. All right, what about our magnetometer and GPS? Those aren't active either. all right, here's something you should probably not spin around indefinitely. But if everything is going well, we take that star tracker input and we update it, our internal state, with more data. Then we take our sun sensor input and update that state. And then we take our magnetometer and GPS and update our internal state. And ultimately, we're outputting a quaternion that is trying to describe where we're supposed to be and rotation speeds for the wheels. And this is our enhanced simulation of nadir point. We were able to take everything that we learned from the aerospace engineers, take all of the components that we updated inside of 42, and turn it into this. I'm going to apologize right off the bat. This is a shorter video than the last one, and so it cuts off a little too early. But like at the beginning, we were just in a random spot, and it is controlled spinning closer to nadir point. And so it's going to cut off right about here. This is a PID-controlled system, and so what it's about to do is go fully flat, dip slightly, and then come back up before becoming totally normal and being able to go and do science. So that's what we've been able to accomplish so far. What's next for this research? Well, we want to be able to connect our software to virtualized hardware. We can already connect to the virtual sensors and actuators, but we want to be able to connect to our FPGAs, our virtualized avionics, and our virtual CPUs to have a full satellite inside of your laptop. And we also want to add command and control. We don't use CFS, we don't use Cosmos, so we need to add a layer so that we can fully do a mission inside of our simulation. And here's a good graph of where we are. We are able to prove out that we can do some application layer simulation, such as this guidance, navigation, and control. That's our ADCS system. We're able to completely do that in our simulation environment, and we're making it so that way we don't have to recompile to run our simulation. We want whatever we are simulating down here on Earth to be the same as what would be out in Cygnus in orbit. But we want to virtualize these avionics, virtualize the FPGA, so that way we can have a full end-to-end simulation environment for our high-fidelity spacecraft simulation. And to conclude, using virtual flat sats makes developing easier. It allowed us to rapidly integrate and test our ADCS algorithm. Throughout this project, there were 2 engineers, myself and one other, where I was focusing on one ADCS mode and he was focused on the other. And we were able to work at the same time without conflicting. If one of us needed to change something on our satellite definition, we could just push that up to Git, pull it down on the other side, so that way we're in lockstep. And we can create a library of sensors and actuators and easily swap them out for future missions. And most importantly, our gold load code that is already existing, can be ported to new simulation environments. Answering the question that was asked yesterday, how hard is it to port something from an existing mission to NOS cubed? It's hard, but it's not impossible. So with that, I will now take any questions.
Thank you, Nathan. Thank you, Nathan. We have a couple of questions that have been posted online. The first one is, do you leverage any modeling standards to enable reuse of simulation models of flight equipment composing the digital twin?
That is a really good question. And I'm not sure, but I will get back to you with that answer. For right now, we've basically been focused on what do we want to model, and those are those 2 ADCS modes, as well as what are the components that we need to model. But I'm happy to chat with you online about it.
What you described, it seemed like you were focused on getting the behavior to look right, but not necessarily, you didn't dive too deep into the numerics of how accurately it mimicked. So I guess first question is, were you able to look at that and get the PID responses, all that to actually look like it should? And then the other part is, that's for a mission that you have data. If you go to a new mission, new profile where you don't have something to compare truth, how do you make sure that you're not introducing new sources of error so that when you launch, the behavior is different than expected?
Both great questions. Let's start with the first one, which was, did we go into and verify not just does it look right, but do the numbers make sense? There was a paper that was published a couple years ago that's about the ADCS system inside of Cygnus, and that gives us a lot of information on what is correct for our PID system, or I'm going to go deeper into the sunpoint mode because, as you can see, it looks a little bit better. The angle between our solar array and the actual sun vector is something that we can both get out of 42 and have seen what actually works inside of this paper. So we're currently working on analyzing those results. I don't have anything for you right now, but we're very hopeful. Does that make sense? Okay, and then the second one, how do we know that we are not introducing error into a new mission? That's a good question. I think our idea, so we are currently working on this Cygnus satellite right here. If we can get that all of our data look the same as what we have on actual flight, we're doing another satellite through this process as well. And so I think once we are confident in those two areas, we'll know what sensors act really close to the actual sensor, and then just kind of extrapolate from there. There's still ultimately going to be hardware-in-the-loop testing, but that we want to push that back to later and do simulation integration as early as possible. But great questions.
Okay, I've got a few more online. How good at timing-wise is simulated hardware compared to the actual flat sat?
If you are talking about the sensors themselves, they're really good. You can specify what frequency you want 42 to pull information from them, and we found that to be very accurate. If you're talking about the FPGAs and the CPUs themselves, we're still working on that, and I will get you an answer as soon as I can. But I've been focused on this side.
Okay, another question is how accurate, well, this may also be related to the virtualization. How accurate are your CPU simulations, and how does the accuracy affect the relationship between simulated satellite performance and real performance?
Another wonderful question. I'll get back to you.
What is the fastest your digital twin has run?
So this one actually runs at about 6. Last time I checked, it was either 6 or 10 times faster. I'm going to go with 6. We can check really quick if someone wants to count with me. Okay, so we're at 12:08. Let's see when it starts. 2001. Okay, that's really fast. So yeah, pretty quick.
Okay, and then there's another question. Configuration-wise, is there a kind of single configuration source file for the whole satellite environment, or can different subsystems be independently configured?
That is another wonderful question. So we are configuring our satellite through 42. 42 allows you to define multiple aspects of your mission. One of those is the satellite itself. All of the components of the satellite have to be defined in what's called an sc.txt file. It's where you list out your actuators, your sensors, and generally how the spacecraft looks. But if you want to change how your spacecraft orbits, like right now we're orbiting around Earth. If we wanted to send Cygnus to Mars, we can say, hey, now you're orbiting around Mars, and it's going to take care of all of those physics properties for us. For the actual implementation of the flight software, you can break that up just like you would in a real satellite, where you have different files that correspond to different subsystems. For us specifically, we just wanted to run our ADCS system all together, but it is easy to split that part out. But your entire satellite is confined to one file.
Any more questions? Thank you.